In this video, we're going to look at springs connected in series and in parallel. So to demonstrate what happens, let's say that we have n springs connected in parallel to a block of mass m, and initially all of these springs were relaxed. So initially I have all springs relaxed. What does that mean? So they are at their equilibrium position, so there should be no restoring force. And then I apply a force F so that finally all springs stretched by how much? By delta x. And I'm doing this by applying this force F, and as a result, initially I had equilibrium, there was no net force acting on this block, and finally I also have equilibrium. The restoring force from the springs is balanced by the force F. So my task is to replace all those n springs with a single spring that, when stretched by an amount delta x, is going to cause equilibrium under the application of this force F. Okay, so let's write down the net force on the x-axis. So as you can see, I have defined the x-axis to the right. The net force on the x-axis is equal to the force F that I'm applying minus the restoring force F1, F2, all the way to Fn. So what are those restoring forces? These are the forces that will develop here, 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 here. So this will be F1, this will be F2, F3, Fn, etc. So those forces will be trying to restore the initial relaxed position. But because I have the force F, external force F applied, those forces are balanced by F and the net force is 0. So I have equilibrium. And for that reason, F is going to be equal to F1 plus F2 plus F3 plus Fn. And those forces are K1 delta x, K2 delta x, K3 delta x, Kn delta x. So I find that the total force, that restoring force applied by those springs will be balanced by F, and it's going to be equal to, in delta x parentheses, K1 plus K2 plus K3 plus Kn, or in other words, I can write it this way: delta x times sum over I 1 to n, where n is the number of springs connected in parallel, Ki. So I look at this scenario where I have the effective spring. The net force in x is F minus the restoring force Fs that I see here. And how much is that restoring force? It's K effective times delta x. So it is F minus Fs is equal to 0. The force that I have to apply is equal in magnitude to Fs in positive I hat direction. It's going to be equal to K effective times delta x. So what I should do is compare this equation with this equation. So I find that if I have an effective spring constant sum over I 1 to n Ki, that is the sum of all the spring constants connected in parallel, for springs connected in parallel, then F is equal to Fs, and the situation is equivalent. So the equivalent spring constant for n springs connected in parallel is basically the sum of the spring constants. So it's going to be sum over I from 1 to n k sub I. And the key issue here is that all of those springs are stretched by the same amount. So I can see that they are all stretched by delta x to reach the equilibrium, the new equilibrium position. Now let's take a look at springs connected in series. Now in this scenario, I have again the block with mass m, and it is initially relaxed springs, so that I would have no restoring force. So I say that initially all springs relaxed, equilibrium, no restoring force. And finally, what I do is I apply this force F. Finally, all springs stretched by a total displacement of delta x. Again, I reach equilibrium. And I would like to replace this scenario with only one spring with an effective spring constant, and the total displacement from equilibrium in the effective spring will be the amount delta x. Okay, so I look at the forces acting on this block. So I see F, and then I'm going to get the restoring force here on the end spring. So that's going to be F sub n. All right. So I call delta x1 displacement from equilibrium of spring 1, and similarly delta xn is displacement from equilibrium of spring n. All right. So I see only two forces acting on my block. The net force on the x-axis is for the block F minus Fn. So that's going to be equal to 0. So the force F that I'm applying is equal to Kn times delta Xn, where delta Xn is the amount with which I have stretched the spring, end spring. Okay, so if I go to any point in between two springs, for example, I'm going to try this point, and I write equilibrium for this point. Let's call this point P. So equilibrium at point P, the net force, this is for the block, and now I do it for point B. Net force in X is going to be equal to K3 delta X3 minus K2 delta X2. So this is going to be equal to 0. So the third spring has been displaced from its relaxed position by delta x3, and the second one by delta x2. So I see these forces acting on the point P. So there is the force F3, and there is the force F2. So that's K2 delta X2, F3 is K3 delta X3. So I have equilibrium at point P. So this is for point P, and because I have equilibrium at point P, I have K3 delta X3 is equal to K2 delta X2. So if I put all of this information together, I have F equals Kn delta Xn. And for the point between nth spring and n minus 1 spring, this would be equal to Kn minus 1 delta X n minus 1. And for example, I have K3 delta X3, K2 delta X2. This will be equal to K1 delta X1 for all the points between the springs. So I can see that the displacement from the relaxed position for the nth spring is F divided by Kn. And for the n minus 1th spring is F divided by Kn minus 1. And if I go like this, for the second one, delta X2 is F divided by K2. And similarly, delta X1 is F divided by K1. Now, because the total displacement from equilibrium for those springs should add up to delta X is equal to delta X1 plus delta X2 plus delta X3 plus delta Xn. I can write for delta X1 F over K1, delta X2 is F over K2, delta Xn is F over Kn. And what is delta X? So I look at this scenario for the effective spring. Now for this scenario, I have net force in X is equal to F minus Fs, the restoring force. So I put the restoring force here, Fs. And the force that I'm applying to get equilibrium should be equal to K effective times delta X, which is the restoring force that I will see on this spring. Okay, so for delta X, I can write here K effective F divided by K effective. So that's delta X. So I can see that the F's cancel, and I'm left with a single equation. 1 over K effective is equal to 1 over K1 plus 1 over K2 plus 1 over Kn. So if I summarize this result, I basically obtain 1 over K effective must be equal to sum over I from 1 to n, 1 over Ki in this scenario. So the reciprocals add up to give me 1 over the effective spring constant. All right, so let's summarize this result. Springs, when the springs are connected in parallel, the effective spring constant is sum over I from 1 to n Ki. When the springs are connected in series, 1 over K effective is equal to sum over I from 1 to n, 1 over Ki. And when springs are connected in parallel, delta X1, delta X2, their displacements, delta Xn, are all the same, delta X. And when springs are connected in series, the displacements add up. So delta x is equal to delta x1 plus delta x2 plus delta x